In exercise 9.16, we are going to show that the rule of existential introduction is not sound if we drop the requirement that x is not a free variable in B. So this is the rule, this rule here, which has the requirement here that x is not a free variable in B. So we're trying to show that if A implies B is satisfied under gamma, then it does not necessarily imply that existence x A implies B is satisfied under gamma if we drop this requirement here. So this essentially means the same thing as, well, this rule here. Without the requirement, we have to show that this rule just by itself doesn't hold. And the way we can do that is you have to show that existence x A implies B is not satisfied by A implies B if x is a free variable in B. So we're saying that if x wasn't a free variable in B, it's still true. Like, this is one of the rules in first order logic. But if this requirement isn't there, then it's not satisfied. So we're going to create a gamma. We're going to create some kind of an interpretation, some structure for which we can show that this this doesn't hold. So we're going to let A be P of x and B be Q of x, where P and Q are unary predicates. And then we're going to create a structure M, which has in this universe we have just the numbers 3, 4, and 5. And P under M is just the set with the number 3, and Q under M is just the set with the numbers 3 and 4. Okay, so we're going to show that for any assignment V, we have that A implies B under M and V is satisfied, is true. So which is just that A implies B is satisfied under, we're going to show that A implies B is satisfied under gamma. I'm going to show that this holds. So for A implies B to be true, we have to have that P of x implies Q of x under M and V is 1. Now this is true if either P of x is evaluated to 0 or Q of x is evaluated to 1. So for P of x to be evaluated to 0, we have to have some x under M and V which is not in P under M. So for this x not be under P under M, it means that the assignment of x, so V of x, is not in P under M, because, as you remember, x here is a free variable, so it will be it will be assigned by V. On the other side, for Q of x to be true, we just have to have it so that x under M and V is in fact in Q under M. And that means that because x here also is a free variable, it's a free variable here, means that V of x is in Q of M. I have to show that this holds for every single assignment V. Now, luckily, we don't have that many elements in our universe, so that's quite easy to check. So first, we can check if V evaluating V to x, evaluating x to 3, makes this hold. So if V of x equals 3, then V of x is in P. So okay, so this one doesn't hold. Then you have to make sure that this one does for it to work. Is 3 in Q? Yes, 3 is in Q. So if we evaluate x to 3, then this is true because this consequent is true. If we evaluate x to be 4, then this first part is true because V of x is not an element in P, so that's good. And for the last one, if we evaluate x to be 5, then this first part also becomes satisfied because 5 is also not an element in P under M. So then we have shown that for every single assignment V, we have that A implies B is satisfied by M. So we've just gone through this here right now. You can read it if you want to see it a bit more formally. So now I have to show that even though this this here is satisfied by M, so it's this holds, that the next part doesn't necessarily hold, that existence x A implies B is not necessarily satisfied by the M that we have chosen. So if it's not satisfied under the M that we have chosen, we're going to just show that there is a valuation under this M, with this M, which does not satisfy existence x A implies B. So they have here created the assignment W such that Wx assigns it assigns a free variable to be 5. So we want to have this to be true. So you want existence x A implies B under M and W to be true, which means that we have existence x P of x, A is P of x, and Q, as you remember, is B. So we have Q of x here. And same as last time, either this needs to be false or this needs to be true. So this needs to be evaluated to 0 or this needs to be evaluated to 1. So on this side, it means that if this is to be 0, we have an existence x here, it means that there does not exist an A in M such that this is true. There's no A which makes this true. If there's no A which makes this true, it means that every single A in M makes this false, where we map, and I'll just underline here that we have an interpretation, an assignment W, such that W maps X to A, and this just means that this X under the assignment W is not in P for every single A, and then that's so every single X assigned to A is not in P, which means that for every single A in M, A is not in P. And this is quite a strong statement because this is just saying that nothing in this universe can be in P. Anything that's in M cannot be in P, and everything in M is just the universe. So P under M has to be the empty set for this to hold. So that's either this has to hold or the other side. On the other side, we had that Q of x and M and W equals 1. So this is true. And this is true if our X under M and assignment W is an element in Q under M. Or W of x is in Q of M and W of x, as we saw up here, that's just 5. So what this essentially on this side is saying is that 5 needs to be an element of Q of M. So either 5 has to be an element of Q of M for this to be true, or P under M has to be the empty set. Now let's have a closer look at what we defined P and Q to being in this structure. Here we had P under M to be the set with 3. So P is not, under M is not the empty set. Then Q does not contain 5. So 5 is not an element in Q under M. Hence, this is not true and this is not true. So neither of these are satisfied, therefore this here, this is false. Okay, so none of these hold, therefore it is not so that existence XA implies B is satisfied by M under this W here. And since it's not satisfied under M under this W here, it's in general not satisfied under M. So we can't say this because we showed that it's not satisfied under this assignment W. And since it's not satisfied under M, we cannot say that A implies B satisfies existence X, A implies B, because A implies B is satisfied under M. Okay, so that was how we went forward to show that, essentially just show the importance of the assignment here. So X, this rule to hold, X cannot be an element in the free variables in B.